Okay, welcome to another Staff 432 video. This video is going to serve kind of a couple purposes. One is it's going to get us used to a different style of videos than a screencast where I'm sort of freehanding notes, like as if it were a chalkboard, but with the handy iPad here, so we can all get accustomed to my handwriting and see if we can tolerate it. And then I'm going to also try to overview the entire course. One of my sort of sub goals of this course is to, how do I say this? Remove some of the hype around machine learning. Said another way is I kind of want to present it as it's kind of boring. I mean, that's not true, but to me, where the excitement from machine learning should come from is sort of the application of it, not necessarily the methods themselves. But that's maybe for you to decide. But that's kind of one of my goals. I think students come into machine learning and be like, this is a super cool thing, but some of the nitty gritty is actually kind of boring, and I think we should sort of accept that. Okay, so I'm gonna make an attempt in this video to completely freehand everything. I've prepared in that I know what the content I want to talk about is, but I haven't prepared any slides or anything. I'm just gonna, with the old stylus here, try to do it all freehand. I think that'll make it a little bit more interesting to watch, and we can all have a chuckle when I make obvious spelling mistakes because they haven't figured out a way to spell check handwritten notes yet, at least not that I'm aware of. Okay, so that you don't have to stare at the top of my head for the whole video, we'll get rid of me, and then we'll get started. Let's see here. Oh gosh. Okay, here we go. So before we even talk about what I'm going to call the different machine learning tasks, I want to sort of make a statement about the sort of this is a video, the sort of data that we're going to be applying these methods to in this class. And it's the type of data you've probably seen a lot in other classes. I just kind of wanted to maybe make some notes about it. So what we're going to be looking at is what we would call tabular data. And really, all that is it's a shorthand for saying this is data that can be presented as sort of rows and columns. So the way you should sort of think about that in your head is something like this. So the sort of data frame notion from R is really useful for thinking about this. So this data has rows, and it has columns. So the rows, each row is a different observation. I'll just write obs. That way I won't misspell observation. And the columns, represent the different attributes that we measured or recorded on these observations, which in statistics we often call variables, which I'll just call vars. So again, each row is an observation. And in this class, for the most part, we're going to assume that those observations are IID, that is independent and identically distributed. That is, we obtained these observations from a random sampling procedure. That's something you should always keep in mind. Not all data will conform to that, but we're sort of making that assumption most of the time in this class. Okay, I'm actually going to go ahead and sort of create like a header row here. And then we'll do something like this. Right. So oftentimes when working with data like this, we sort of name the columns. So I'm going to name them something like x1, x2, x3, x4, and x5. And then, oh no. There's data stored in these columns. So one sort of important thing that we're going to want to keep in mind is the type of data that each variable is. So broadly speaking, in this class, every variable is going to fall into one of two categories. It'll either be numeric or categorical. We could further break down these categories, but talking about categories and categorical, we could further break down these two types of data, but we're not going to worry about that too much. Basically, the general idea here is that numeric data stores numbers. That could be, say something you could measure, right? So like the temperature of a human, or the number of mistakes I make in this video. That's numeric type data. Or we could look at categorical data, which essentially places observations into different categories. So maybe observations are pets, and category. So one of the variables would be like, is it a dog or a cat or a bird, something like that. So, generally I sort of assume this is a concept that you've seen before, but playing with these two different types is going to be sort of important for understanding what we're about to talk about. Okay. So everything we do in this class will be with data that can be represented in this form. Data exists outside of this form. You could sort of think of like audio data or video data or image data, and various other things. But oftentimes you could translate it into this tabular setup. But that's something that's sort of outside of this class. We're going to talk about tabular data. Okay. So we want to do stuff with this. So those things that we're going to do in this class are going to be machine learning. And within machine learning, we're going to talk about what we call machine learning tasks, which I will call ML tasks. So in this class, we're going to talk about two broad categories of tasks. One, oh boy, that's a terrible arrow. One is called supervised. And very cleverly, the other is called unsupervised. So the vast majority of this class, we're going to focus on the supervised learning task. And when we dip into the unsupervised learning task, it will mostly be in service of a later supervised task, but more on that much later. But generally, these are the two big areas within machine learning. You have supervised tasks and unsupervised tasks. More on what that even is in a second. But there are other forms of machine learning. You may have heard of something called semi-supervised learning. You may have heard of something called reinforcement learning. Those are a bit outside of the scope of this course. I think you'd want to sort of understand these two more basic tasks before you move into things like that. Right. And then so before we even define what these two things are, within each of these sort of large tasks, there are sort of subtasks that we're going to focus on. So within supervised, we're going to look at what we call the regression task and also the classification task. These two, being that they're both supervised, share a lot of similarities, but they have sort of one key difference. And then unsupervised, there are a lot of things that fall into this category. We're going to specifically look at 3 to 4. So the main one, in my opinion, would be called density estimation. And really, in a lot of ways, density estimation could sometimes be thought of as a precursor task to some of these other ones we're going to talk about, but it's worth mentioning as its own thing. Let's see. We're also going to talk about outlier detection. Clustering will probably be the biggest one within the unsupervised task, and we'll also talk about dimension reduction. So the dimension reduction, we're probably not going to talk about a ton on its own, but we will talk about sort of how to use it as part of a supervised learning task. But again, much more on that much later. So what I want to do is I want to now go through and give sort of a brief description of each of these as it pertains to tabular data. So let's talk about supervised versus unsupervised real quick. The distinction here is pretty simple. So we have our tabular data here. And let's say we have variables x1, x2, x3, and x4. Okay, so if we do not have a response variable, sort of a target variable that we're most interested in, hopefully that's a concept that is familiar from previous courses, then we would be in the unsupervised. So if we sort of flip that definition and say, well, instead of this variable being called x4, I'm going to give it a new name. I'm going to call it y, and I'm going to sort of anoint it as the response variable. This is the thing we care about the most. Well, now we're in supervised learning. So, yeah, that's it. It's pretty simple, but there's a lot more to it, which we'll see as we talk about the individual tasks. So the first one I want to talk about is the regression task. So I imagine that if you're in STAT 432, you've already done quite a lot of regression, either in STAT 420 or STAT 425, or perhaps some other course. So if we're talking about doing regression on tabular data, we're probably going to have a data set that looks something like this. We have some variables and then a response variable y. And I'm actually going to maybe write down some data here. So importantly, in the regression task, as we're going to define it, the y variable, which again is the response, which means that we're doing a supervised task. In regression, this response variable needs to be numeric. So we have like, I don't know, 1.1, 2.3, yada, 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 right? So that's the big thing here, is we have a numeric response variable. And then the covariates, which you've probably called them before, which in machine learning terms, we're going to call something else. We're going to call the other variables the feature variables. You may also see these referred to as covariates. You might also hear them referred to as predictors, but that's going to get a little bit confusing considering we're doing a lot of prediction in this class. So we're going to stick to the machine learning terminology here of feature variables. So I should call these features, plural. And the feature variables in the regression task, we don't really care so much if they're numeric or categorical. They can be either, so I'm just going to fill them in with dots. Depending on the method we use to do the regression later on, we might care a little bit about whether or not it's categorical. We might have to do a little bit of conversion to numeric ahead of time, but that's for a much later time. And then just really quickly, visually. So let's say we had some data that looks like this. Let's say we had a single variable x and then a response variable y. And let's say the data looked something like this, our goal is to say, well, let's say we get a new data point and we know the x value is here. So I'll call this x sub 0 for like a new value. We want to know, well, what y value would we predict? And based on looking at this, I would guess something like this. We're going to go a step further and say, well, what we really want to do is for every possible x value, we want a good guess for a new y. But said more statistically, and we'll learn the reason for this later, what we really want is an estimate of the mean of y at that x. So what we really want to do is maybe learn a function that looks something like that. So this is the first time I sort of brought up this prediction notion, which is what we're all about in this class. So what we really want to do is, this is what I'm going to call the old data, right? And the old data, we're going to give more technical terms for this later. I'm not going to refer to old and new all the time. But the old data, we have all of the feature data. We have access to all of the feature variables and the response variable. But then with some new data, we don't have access to the response anymore. We only have access to, that was exactly not what I wanted to draw. We only have access to the features, and with those features, we want to make a prediction for what y would be. So that's kind of, I mean, really, this is actually kind of a one-slide summary of the whole course. We have some data. It has both the features and the response. We want to learn this function that will then allow us with new data that has a missing response to make a best guess for that response. Okay, so that's regression in a nutshell. Much more of that throughout the course. So again, so we're talking about the supervised task right now, and sort of the parallel to regression is this notion of classification. So, right, classification. So classification, it's just regression. And in many ways, sometimes it is technically a regression, but I'm going to call it classification. So the only difference is that instead of that numeric response, we have a categorical response. I'm going to see how good I am with the iPad here for a second. Wow, okay. Smarter than I thought. All right, so let's modify this now. So now instead of having numbers, a numeric response variable, we're going to have a categorical response variable. So instead of numbers, we'll have categories, which I'll represent by like A's, B's, and C's, yada, yada, yada. And now I need to change this to say the response is categorical. Cool. And again, this is also supervised. We have a response variable, but now instead of it being numeric, it's categorical. Cool. Again, we can have any number of features, and they can be either numeric or categorical. And then, we're going to fit some model, we haven't really talked about what that means, to the data we have with the response. And then with the new data, where we only have feature information, we want to make, I guess let's call it a classification. That is, which of these categories do we think that this observation belongs to? So I'm going to kind of try to draw this. The picture looks a little bit different. So let's say that this axis is now x1 and this axis is x2. So we have a two feature problem, not quite mirroring the data here. And let's say that there are two possible categories. So I'll use these blue circles to denote observations that have category blue. And then I'll use these gray circles to denote observations that have category gray, right? So what we want to do in the classification task is say, well, let's say I see a new observation right here with this black, well, I'll make it an X actually. So at this black X, do I think that this should be category gray or category blue? And you should probably be screaming at your computer right now and saying, well, that should be category gray. But maybe we want to predict instead at this x1 comma x2 value. And now you're going to scream blue, blue, it should be blue. And then what if I say, I don't know, how about right here? Now you're going to be like, well, I don't know. It could probably be either. So this gets me to sort of an important point here. So ultimately, with classification tasks, often you want to say, hey, I have this new data point. I have the feature information on it. I want to say which of the two possible categories, or however many categories, it could be more than two, that it should belong to. But what we're going to talk about more so than that is not which category does it belong to, or do we think it belongs to, but instead, what is the probability that it belongs to a particular category? So this first X I drew, this is probably, we should probably say, well, it has a high probability of being gray, low probability of being blue. This one, high probability of being blue, low probability of being gray. And that last one, we should probably have a result that says, well, you know, there's a decent probability that it is either blue or gray. And that's what we're going to talk about quite a lot in this course when we get to classification. So these two tasks we just talked about, regression and classification, the key idea here is that we're learning something conditioned on feature information. If that doesn't mean anything to you yet, that's okay. That's what we're going to talk about a lot. But essentially, you could boil supervised learning down to we're learning some feature of a conditional distribution of the response variable. If you understand what that means right now, maybe this class is a little too easy for you and you should consider 542, but if not, you're in the right place. That's what we're going to talk about. Okay. So, and again, I should say we're focusing on supervised learning in this class. So this regression slide, this is what we're going to talk about for the first few weeks. Then we're going to spend a ton of time on classification, especially that bit about probability that I mentioned. But then let's go back here. Okay, so now on to supervised learning. So, supervised learning. Let's talk about density estimation. Okay, so we said that this is unsupervised, which I'll often just call unsup so I don't spell things wrong. So, big difference between supervised and unsupervised is that now we no longer have a response variable. So let's say we have, I don't know, 4 variables. And for the sake of simplicity of talking about this, we'll just assume they're all numeric and they don't necessarily have to, right? So ultimately, what we want to learn, and this is honestly, if we could just do this, we wouldn't even need all these more specific tasks, but this is hard, so this is why we don't necessarily do directly this. What I want to do is say, well, I'm going to model this by 4 random variables, x1, x2, x3, and x4. And the thing I want to learn is their joint distribution. So this is either extremely hard or extremely easy. The general idea here is that if you have not a ton of variables and a huge amount of data, you might be able to do something here. If you don't have that much data, it's probably very hard. What is a lot of data? Hard to say. So this would require a lot more thought to really dig into, but we'll get there later. This task is sort of one that we'll almost never do by itself, but it'll underlie some of the things I'm about to say about some other tasks. Okay, so sort of skipping that for now, let's talk about outlier detection. So again, we're unsupervised. So let's say we have some data with just an x1 and an x2, and I'm actually gonna make up some numbers this time. So let's say that here we have numbers that look like this, yada yada yada, and let's say x2 looks more like this. Those are 5s in case you can't read my handwriting. Okay, so here's some data. And again, let's sort of call that the old data. And then let's say I observe a new piece of data. Actually, 2 new pieces of data. So let's say I observe something like 2.3 comma 5.4. And then I also observe 1.5 comma 10.9. So the question we're sort of asking in outlier detection is, do you think this observation was generated by the same process that these observations were? I think most of you would say yes to that one. If I ask the same question, is this observation generated from the same process as this above data, I think you would all probably say no. And sort of one of the, so this is a tie-in to the density estimation. So if we had, the distribution of x1 comma x2, we could simply see what the densities were for these 2 new points, and if it's really low, that's possibly an outlier. So visually, and this is not going to be the same data, so it would maybe look more so like this. So let's say we had data that looks like that, and I say, hey, could this data point have been generated by the same process? And you'll say, yeah, sure. If I say, I should draw an X to make it clear. If I say, hey, was this data point generated from the same process? You'd probably say no. So yeah, that's outlier detection. One note here is that I want to be really careful. Oftentimes, for various reasons, when students detect outliers, they remove them. Without getting into the details, I want to say you probably shouldn't do that unless you have a very good reason to, and that's one of the things we're going to talk about here. I think outliers are often a little bit difficult to understand, and we need a lot more context to talk about it, but just because you can detect an outlier does not mean it's bad data and you should get rid of it, but more on that later. Okay, clustering. So clustering, again, we're still in the unsupervised world. I'm not even going to write down the data frame. I'm just going to go straight to a picture. So again, let's say we have some variables x1 and x2, and I got to try to do this really well here. So let's say when we plot the data, it looks, yeah, something like this. We'll just do a really simple example. So the goal of clustering is to say, hey, I want to group this data. So I want each of the observations, maybe I should draw a data frame on the side here. So basically, I want to say, hey, I want to group this data together. So we want to sort of say, maybe this observation, and this observation go together. and this observation, this observation, this observation go together, and maybe say this observation is in a group by itself if we were going to try to put the rows into 3 groups. I use 3 groups because this image over here pretty clearly says, well, I think these things should be grouped together. I think these things should be grouped together. And I think these things should be grouped together. This example that I drew is trivially obvious, and we don't need any method to do it other than we can plot the data and as a human do it. But imagine, well, hey, we have more than 2 variables, so now we can't really plot it. Maybe the data isn't so well separated, so things aren't so easy. Like this graphic screams, oh, there's 3 groups, but when you're just staring at numbers and high dimensions, even the number of groups that there would be difficult. So much more on that later, but that's a general idea. Without using like a label that already exists in the data, which is kind of what classification is. So these two are really related. It's sort of like saying we're doing classification, but we didn't have this response variable column. We're just guessing based on the data itself. We're not utilizing the fact that we previously saw some labels. We don't even ahead of time see labels here. We're just directly grouping data. So that's harder. Okay. So lastly, a bit about dimension reduction. So again, I'm not going to belabor the point here. Let's say that we had data. No, I want to go big here. Let's say we had data that looked like this. Yeah. So let's say we had 10,000 variables. What I want to do is reduce that. Dimension reduction. Statisticians are very clever at naming things. I'll call this x star 1, x star 2, x star 3, and x star 4. So I went from a data set that had 10,000 variables to a data set that only has 4 variables. And I want to do that in a way that retains most of the information from the original data. So this is kind of like a compression type thing. And where this will come in real handy is when we're doing a supervised task that also has a y variable. So it'll decrease the inputs to our supervised method. And that's why I sort of, even though the technique itself is unsupervised, we often use this within a supervised task. We kind of merge them together. Okay. Yeah. So let's end the video on this slide here. So again, these are the sort of things we're going to learn how to do in this class. We're going to largely focus on supervised learning. Probably within that, focus a lot on classification, as you've already seen a lot of regression. When we talk about regression, we're just going to really focus on this prediction paradigm that you may not have focused on previously. But yeah, that's the idea. So I would hope that at the end of this video, you have picked up on a couple things, but are feeling like, oh, I don't know what's going on yet. Here, I'll talk to the camera for a bit here. You should be like, hey, that was a lot. I don't know what's going on here. And that's kind of the point. So everything I just said here is what we're going to be learning throughout the semester. So if the only thing you got out of this lecture was these terms exist and maybe like a really simplistic view of like regression is something where there is a response variable with a numeric response, that's all we're trying to get you to learn in this video. Details, I mean, basically this course is going to be fill in the blanks. What you don't understand from this video is what we're going to talk about in this course. Okay, I talked a lot, which means it's time to end this video. If you made it to the end, as always, good job, and I will see you in the next video.